We're now going to take a look at how to handle processes that change with time. And a process that changes with time is called a dynamic process. And with a dynamic process, we need to be able to handle the simultaneous mass and energy balances. So we're going to take a look at an example where we can do both mass and energy balances simultaneously. Say, for instance, I have a tank that's equipped with a heater, and I have an inlet stream coming into my tank. And there's also an outlet port on my tank, but it's at a position near the top of the tank. And as I turn on my fluid, the tank will slowly begin to fill until I reach the point where it reaches the outlet port. At that point, everything that I put into my tank will leave my tank, and I reach a steady state in terms of the mass of the material that's in my tank. Let's also say that I don't turn on the heater until the tank is full. I can change my mind and turn on the heater at any other time, but we'll go with that for the time being. So let's put some dimensions and variables onto our figure. The mass flow rate in, m dot n, will be the stream coming into my tank. That leaving we'll call m dot out. And I'll say that the height of the outlet port on my tank is letter H, and the diameter of my tank is letter D. We'll use capital letter M as the mass of the liquid in the tank at any time. And we're going to first look at, let's write a differential mass balance. So the differential mass balance would be the change in mass with respect to time of the liquid inside my tank. And that will equal the mass flow rate in minus the mass flow rate out. And at some time 0, we'll say that there is m0 kilograms of liquid in my tank. We'll also use the parameters that if the level in the tank is below H, there's no flow rate coming out, so m dot out would be 0. However, if the level reaches H, m dot out is equal to m dot in. So how do we calculate the level in the tank? Well, that's just given by the mass of the liquid in the tank divided by the fluid density and divided by the cross-sectional area. So the volume in my tank is capital letter M over rho, and the area of my tank is pi d squared over 4. So the volume over the area will give me the level that I'm seeking. So as long as this level is less than the overall tank height h, I will not have any flow rate coming out. But as soon as the level reaches h, then I'll have flow rate coming out, and that will equal the flow rate coming in. Let's look at it from an energy point of view. And so just like a mass balance, the energy balance looks just the same, except I have an additional term. We'll say that the change in energy of my system, and my system is the liquid inside my tank, is equal to the energy coming in by flow minus the energy leaving by flow plus the energy input by the environment, which I call Q dot, and that's delivered by the heater. Now let's break down each of those terms into something that we can recognize. The energy of my system is just equal to the mass of my system, capital letter M. Note that that M changes with time, times the heat capacity at constant volume. And then it will be multiplied by the temperature of my system minus the reference temperature. Remember, we never really truly know energy. We can only know an energy difference, and so we're going to choose a reference temperature that we're going to compare all our energy states to. At the initial time, T equals 0, we'll say the temperature is equal to T0. Now let's look at our energy coming in by flow terms. The energy coming in will just be the mass flow rate coming in, m dot, times the heat capacity at constant pressure, times the inlet temperature minus the same reference temperature. Energy leaving is just equal to the mass flow rate out times the heat capacity at constant pressure, times the temperature minus the reference temperature. Now, the temperature coming out, T, is the same T as we have when we look at the energy of our system. And the reason being is we're going to assume that our tank is well mixed. So the temperature coming out with this mass is equal to the same temperature in my tank T at any given time. Now we're going to apply some of our differential calculus to get this equation set up correctly. So the change in energy of my system, I'm going to take the derivative of the energy of my system with respect to time. So I'm going to look at this equation here. And when I look at it, I have two variables that are changing with time. One is the mass, because while I'm filling it up, the mass is also changing. And again, the temperature changes with time. So when we have a product of two variables that change with time, taking the derivative, we have to use a chain rule. So we hold one variable constant and take the derivative of the other, and then hold the other variable constant and take the derivative of that other variable. So we're going to hold the mass times the heat capacity, constant volume constant, and take the derivative of the terms in the parentheses. Note that Tref does not change with time, so the derivative of it is 0. So we have the differential of temperature with time dt. Now I'll hold that constant and take the derivative with respect to mass. So I'll have a constant heat capacity at constant volume. That will not change with time, times T minus Tref. And then the derivative of mass with respect to time is dm dt. And that will equal the energy coming in by flow, which is now m dot n Cp times the temperature in minus the reference temperature, minus the mass flow rate out, times the heat capacity, constant pressure, times the temperature minus the reference temperature, plus Q dot. Let's rearrange our equation because I want to look at the change in temperature with respect to time. And so all I did was a little bit of algebra and rearranging that same equation. And so we have our change in temperature with respect to time. This term will be equal to our energy input by flow. This is the energy output by flow. This will be the ratio of the heat input Q dot divided by the mass flow rate, or the mass of the system, times the heat capacity constant volume minus this term here. When this tank reaches the level H, we'll see that the change in mass with respect to time will then become 0, and this term will drop out. I want to draw your attention to a situation where we might have no material in the tank at the initial time t. In that case, m would be 0. And so we cannot use this equation by putting m equal to 0 in this equation because we cannot divide by a value of 0. So to get around this, we're going to put in just a little bit of material to start off our problem so that we don't run into that situation. So let's take a look at our equations once more, getting them all organized on the same sheet. The change in mass with respect to time is just equal to the mass flow rate in minus the mass flow rate out. At time equals 0, the mass of our system is some value m0. Our change in temperature with respect to time is given by this equation. And the temperature at time equals 0 is T0. I'm going to now substitute the value of dm dt, which is just equal to the mass flow rate in minus the mass flow rate out. So that's the only thing that I've done differently. And I want to remember that when time is equal to 0, we want to have just a small value of m in our problem, because when we go to a spreadsheet solution, we want to make sure that this does not cause us any problems. So we'll just throw a splash of water into our tank before we turn on our analysis for this. And remember some of our conditions. If our level is less than the outlet height, then our outlet flow rate will be the same as our heat rate. In this case, it will be 0. If the level equals h, the mass flow rate out will equal the mass flow rate in, and the value of the heat rate, Q dot, will be equal to whatever we desire to put into our tank. Now, when we want to solve these equations simultaneously, we're going to have to collect a couple of variables and some information about the material in our tank. The first one would be the heat capacity at constant pressure. And for liquids, that is usually something that doesn't change with temperature. And so all we need is the heat capacity, C sub P. For a liquid, the heat capacity at constant volume is nearly identical to the heat capacity at constant pressure. So in this case, CV will equal CP. And if our system is water, the value of the heat capacity at constant pressure is just equal to 4.18 kilojoules per kilogram degree Celsius. Another parameter that we have to be aware of is the density of the liquid. Now, although it is not very large, but the density of liquids change with temperature. And so I know that my liquid coming in, its temperature will increase if I supply heat to it. And I need to find out, how does density change with temperature, so that I can use that in my equations. And so I gathered some data off the internet, looking up the density of water at various temperatures. And at low temperatures, we'll find that the density of water is pretty close to 1,000 kilograms per cubic meter. Okay, but as the temperature starts to increase, we find that the density starts to decrease. And as we approach the value of 100 degrees C, our density is close to 960 kilograms per cubic meter. So we want that to be reflected in our equations. Simple tool that we can use with an Excel is do a trendline fit for the density as a function of temperature. And since I could tell that the data was curved, I use a second order model where the density at any temperature T is given by a coefficient negative 0.0035 times the temperature squared minus 0.0705 times the temperature plus a constant value of 1000.3. So now I have the ability to determine what the density of water is at any given temperature. We're now going to use an Excel file which is called YS Utilities 2018. This is an Excel file that contains macros that will solve differential equations simultaneously so that we don't need any sophisticated software like MATLAB when we look at differential equations. When we start out, we have a number of different menus and different macro buttons on this, but I just wanted to point out a few things that are important to our type of problem and how to use this. So if we look at our menu, I have a number of things listed here. One is number of differential equations, and we would put in how many differential equations that we have. Remember this, if you even put in too few differential equations, we can add it later. So let's say, since we're doing a mass and energy balance, we have two differential equations, but I'm only going to use one differential equation for the time being. Then it asks us, what is the initial value of time? In almost every case, our initial value of time is 0. And then the final value of time. Okay, so how long is you going to have this program run? And we're going to do is select a time, and if we need to make it longer, we can always change it. But let's put in, say, 100 time units. In this case, our time units will set to be equal in seconds. The next thing is, what value of time step are we going to use in the integration? This is a numerical integrator. And if we choose a very, very small time step, our accuracy increases, but the number of computations that have to be done also increase as well. This requires a long time to solve. If we choose a value of delta t to be too large, then it solves the problem quickly, but we introduce more error into the problem. So this is something that we'll have to adjust and see how well it works. I also have a cell called output interval. This output interval is how often do I want to display a value. If I have, say, 0 to 100 seconds for my initial and final value of t, I may only be interested in displaying an output, say, every 5 seconds. If I have it every tenth of a second, I'd end up with 1,000 points. Not necessary for me to have that many. So we would then select what our output interval would be. Integration method. There are various different models we can choose from. Euler, or some people pronounce it Euler, is a very simple model that can integrate equations as long as they don't change very fast. So it has very low accuracy on problems when they change steeply or if they reverse directions with respect to time. However, it calculates things very quickly. Hune is a little better than Euler. A Runge-Kutta of fourth order is better still. Fifth order is better still. We're going to stay with a fifth order Runge-Kutta model. And this one has an adaptive step size control. This means that even if I guess the wrong value of delta t, it will adjust it automatically to give me the accuracy I desire. So this is a good method to use, and we'll stick with that. We got a couple of other things as well. Output variables. I have differential equations, but I might be interested in recording other variables as a function of time as well. And so I can include this to have maybe many things displayed at the same time. The remaining three, the dead time variables, integrated variables, and derivative variables, don't concern yourself with these just yet. These are part of a process control portion, and we don't need to worry about it at the time being. So let's just take a look at having one differential equation. Initial value at time is 0, final is 100 seconds. I'll throw out a value of delta t equal to 0.1. And let's say my output interval. Oh, I think I'll have things every 5 seconds in this case. All right. So once I have these variables, I'm going to click on Run Initial Setup. And it goes through a little program that does that. And here, notice I have a couple things. One is this variable x, y1, dy, dx1. Okay. X is a generic term. I'm going to change that to time just by typing it in. And I'm going to include seconds as my units. Now Y1, let's just say we're going to look at the mass balance. So Y1 would be the mass of liquid in my tank M. The derivative of that variable is just equal to dm dt. So I'm going to have a column that has my mass and a column with the change in mass with respect to time. I'm going to put an initial value of m. I'm going to say is, say, 0.1 kilograms. Now I need to calculate the derivative. So I can put in, m in. Let's just say, well, maybe 5 kilograms per second. I'll say m out. For right now, we'll put it 0 kilograms per second. We're going to change this later on. I just wanted to show you how things can be set up in a relatively quick time. So I put in my value of m dot in, m dot out. So my change in mass with respect to time is just equal to the mass flow rate in minus the mass flow rate out. And I'll hit enter. So if m dot out is 0 and m dot in is 5, the change in mass with respect to time is just 5 kilograms per second. Now I'll click on Integrate Equations. But before I do, need to tell it what time points I want to use. So I'm going to click on this red button called Fill Time Points. And if I go down, it immediately goes from 0 to 100, output equal to 5. Now I can hit Integrate Equations. And so here we have it integrating the equations that each individual time is at 5 seconds, I'm at 25.1 kilograms. 100 seconds, I'm at 500.1 kilograms. And so I have this integrating feature in Excel that will allow me to solve differential equations. Let's now look at how we can take our tank a little bit further and record the height as a function of the mass inside the tank. If we look at the height equation, it's equal to the mass of the fluid in the tank at any time t, which we call letter m, divided by the density of the fluid, divided by the cross-sectional area of the tank. Let's set our tank to have a diameter of 2 meters, a height of 2 meters, and our area is just the pi times the diameter squared over 4. I'm going to calculate the density as a function of temperature using that equation that we created a couple slides ago. And it's a function of temperature. And that equation said that the density is 1000.3 minus 0.075 times the temperature. In this case, I'm just going to say the temperature right now is 25 degrees C. And then also minus 0.0035 times the temperature squared. So at 25 degrees C, my density is 996.35 kilograms per cubic meter. Now I want to record the height as a function of time, and so I'm going to do this by creating an output variable. So we're going to scroll up and look at adding an output variable. I'll click on this little menu here, and notice that it created an output variable, which is the letter Z, Z1 for this case. Well, this will actually be my height in my tank, and I'll put in meters as my units. So let's put in the equation for calculating the height inside my tank. Well, the height is equal to the mass of the fluid in the tank divided by the fluid density and divided by the cross-sectional area, which we've just calculated. So currently, right now, with just 0.1 kilograms of liquid in my tank, I have a very small height. Okay. Now, as I start filling the tank, the height will start to grow. And when I reach the height of 2 meters, my outlet flow, instead of being 0, it's going to be equal to the mass flow rate in. So we're going to put in an equation that says when the height is less than 2 meters, the outlet flow is 0. However, when it's 2 meters or higher, it's actually equal to the mass flow rate out. And I can do this with a simple if statement. I'll put in an equal sign. Okay, and I'll put in an if. Then I'll put in if the height, click on the height in this cell, is less than, I'll actually click on the cell that has the height. So if it's less than 2 meters, then it's going to be 0. Otherwise, it's going to equal the mass flow rate out, which is, in this case, the cell L5. So I'll close my parentheses. So right now, with my height in my tank being very small, my outlet flow will be 0. Okay, and we're calculating the height as a function of time. So at some point in the future, our height will reach 2 meters, and then that outlet flow should go from 0 kilograms per second to the value of the inlet flow, which I have right now set at 5 kilograms per second. So let's follow this by integrating my equations, and click on that, and it's doing its calculations. And let's take a peek at our results by scrolling around. So we notice from going from 0 seconds to 100 seconds, my height didn't change by a whole lot. It's only 0.16 meters. And that's because we're not running for a long enough time. So we're going to change our final value of time. Instead of being 1,000 or 100 seconds, we're going to make it 2,000 seconds. And I don't want to have an interval of every 5 seconds. That will just generate a lot of unnecessary data. So I'm going to have it output every 100 seconds. Now, since I changed my time, I got to recalculate my time points. So I'll click on that, fill time points. And now you can see that my time is going to go from 0 to 2,000 seconds. I can now integrate my equation by clicking on that cell. And now we're looking at the mass inside the tank as a function of time, but also the height in my tank as a function of time. And let's take a look at what happens. So as we see, as we proceed through the time, somewhere in between 1,200 seconds and 1,300 seconds, we actually see that the height will reach 2 meters. At that point, my derivative, the change in mass with respect to time, switches from 5 kilograms per second to 0 because my mass flow rate out will equal my mass flow rate in. So we can now see how the height changes with time. At somewhere in between 1200 and 1300 seconds, we reach a steady state. Let's now take a look at adding the energy balance to our process. If we recall from the energy balance equation, we have a change in temperature with respect to time is equal to mass flow rate in times heat capacity times the difference between inlet temperature and reference temperature divided by the total mass divided by the heat capacity constant volume, and then the other terms as well. So we're going to need some information about the process. One is the heat capacity at constant pressure and the heat capacity at constant volume. Well, if our system is water, the heat capacity at constant pressure is 4.18 kilojoules per kilogram degree Celsius. And for most liquids, the heat capacity at constant volume is the same as the heat capacity at constant pressure. And we'll be dealing with a liquid state, so we'll use the same value. We're also going to need to know what the inlet temperature is. So let's say it's 30 degrees Celsius. And we're going to select a reference temperature of 25 degrees C for this problem. Our mass flow rate out is already determined by a differential equation, so we don't have to worry about him. And the temperature in the tank, if it's well mixed, will equal the temperature leaving. So the term dealing with the mass flow rate out, that T would equal the tank temperature. Then we'll have a heat term, Q dot, and in our case, I'll just call that 1400 kilojoules per second, and this can be varied depending on what the heat output of our heater is. And then finally, we have the last term in the equation. So now I have to insert a new differential equation, and just like I inserted an output equation, I can hit add differential equation and end up with a term for Y2, and that's going to be my tank temperature, which I'll call T, and the derivative I'll just call dt. So that's the derivative with respect to time. And we'll say our initial temperature in my tank is 25 degrees C. So I have the temperature in degrees C. Now I have to put in my equation for the derivative. So that's going to be equal to our mass flow rate in, which I'll click that term, times the heat capacity at constant pressure, times my inlet temperature. I'll click on the Tn, 30 degrees C, minus my reference temperature. Close my parentheses. Divided by the mass of my tank, divided by the heat capacity at constant volume. So I need to select the mass in my tank, which is M, and divide that by my CV term here. Now I'm going to subtract the mass flow rate out, leaving. So I'll click on that cell. And it's going to be times the heat capacity at constant pressure times the outlet temperature, which will be the cell here, minus the reference temperature, 25, divided by the mass times the CV, click on the mass, divide that by heat capacity at constant volume. Now I'm going to add my heat term, and at the present time, I'm going to click on the cell that says Q max 1400 kilojoules. I'm going to make a change to that a little bit later on, but we'll just select that cell so it's there. And I'm going to divide by the mass of the liquid in the tank. Divide that by the heat capacity at constant volume. And then I'm going to subtract the final term, the temperature minus Tref. Temperature minus Tref times the difference in mass flow rate, in minus out. And divide that by the mass inside my tank M. So if we entered our equations incorrectly, we should be able to see that we can calculate what that derivative is. Now I talked about this Qmax term. Right now it's set at 1400 kilojoules per second. But let's say we're going to leave the heater on only when we've reached the height equal to 2 meters. Below the 2 meter mark, we're going to turn the heater off. So I'm going to put in an expression for this term. I'll just say that instead of being equal to 1400, I'll put an equal sign. And if the level is below, I'll click on my height. If it's below the 2 meter mark, then it's 0. Otherwise, I'll put in 1400 for right now. So what's going to happen is, as I fill up the tank, no heat will be turned on. But once I start reaching the outlet port of my tank, then it should go to 1400 kilojoules per second. So let's integrate our equation and see how this works. So I'll click the button, Integrate Equations, and we'll look at how our temperature changes with time and also the height changes with time, and see how that works out for us. So let's take a look at our data. Now notice that my temperature, we originally were at 25 degrees C, but notice that the liquid I was putting in is at 30 degrees C. So we'll see an initial jump in temperature to 30 degrees C. And then when I reach the point where I have 2 meters in my tank, my heater kicks on. And so I start seeing a rise in temperature. Also note that even after 2,000 seconds, although my height has reached the 2 meter mark, my temperature is still rising. So let's expand my time frame from 2,000 seconds, and let's change it to, say, 4,000 seconds. And I'll change my output to every 200 seconds I want an output. That's not necessary. However, we just don't want to generate a lot of data. So I'm going to refill my time points. Integrate my equations. So now it's going to be giving the expanded time frame, and we'll see how our temperature, what it will become when we expand our time frame. So let's go back to our data after it's run. And I notice that even after 4,000 seconds, I have still an increase in temperature. So we haven't reached steady state yet. Okay, so we would want to run our tank a little bit longer in order to see that steady state happen. But this is how we add heat into our process and look at the change in temperature with respect to time. Let's expand our time frame out to, say, 6,000 seconds. I'll click on my fill time points, and I'll integrate the equations. So now we'll go for a much longer period of time to see how close we are at steady state with temperature. Note that with mass, we reach steady state as soon as my outlet flow became the same as my inlet flow when we reached the outlet port. So at 6,000 seconds, I'm seeing a slight increase in temperature, but it's beginning to stabilize off. So we might, if we extended this even longer, reach a point where we have a temperature close to the steady state temperature. A better way of seeing this happen is if we insert a graph. I'll put in an XY plot, and I'll plot my temperature versus time. So my X values are given by my time. And my Y values are given by my temperature. Click OK. Let's take a look at our graph here. So here we see initially we're at 25 degrees C. Then when we turn on our water flow into the tank, it immediately goes up to the 30 degrees Celsius and holds there until we start adding heat to the process. And as we follow the temperature with respect to time, that looks like we're almost leveling off to, say, something maybe around 96 degrees C. And so this is how we can look at the dynamics of this process with respect to the temperature and time.